Here we go. Well, hey everybody, once again, welcome to Astronomy Daily Live, where every single day we gather together, bunch of friends, get together on sort of our virtual porch here and sit back, drop pens on the ground, and grab our favorite consumable of choice and think and talk astronomical things for at least a little while or so. I'm gonna aim for maybe a shorter live stream again. I'm had sort of a busy day, a little worn out, but you know, what tends to happen, right, is that I sort of get started with this and I start to think about my favorite topic, right? My favorite topic of all time. And the adrenaline starts going, right? Pumping and going and, more and more and more. And usually, before we know it, it's past an hour and it's like, wow. So, yeah, well, we'll see how those kinds of things go. This is just a fun, casual get together of friends every single day, and like to keep it about an hour, sometimes a little bit more, sometimes a little bit less. We'll see how it goes. So I'm gonna look at the chat really quick. Okay, all is well there. So in the panel once again is Tom. Hey there, Tom.
Hey, Cosmic. How you doing?
Everything
hey, everybody out there in the lettuce bin.
In the lettuce bin. Let us roll around in the lettuce bin. Well, yeah. I I think that the people who are part of this live stream are extremely creative, and so you know uh, you know silly things like that definitely are like thumbs up. So yeah. I think I told the story a little while ago about the handle cosmic lettuce, and I should probably do that from time to time. I'm definitely not going to do it today, but I should probably give that origin story once again. So just for new people and to sort of remind myself where that came from too. Because I mean it's there isn't anything crazy about it or anything. It just I had to come up with some kind of name, and I did, and that's it. So anyway, well. I'm glad that things are well with Tom. We also have Bobby on the panel. Hey there, Bobby.
Hey.
Everything well over there?
Yep, all is well here.
Good. Yeah, we're still experiencing a little bit of rain here. I heard up in Colorado they got a bunch of snow. So, wow, that's absolutely amazing. Hey there, Andy. I see you in the chat, along with Mr. Gaming. Mr. Gaming, I want to see. Okay, yeah. Well, it's possible. It's possible that what you say is true, but people with wrenches may do things with that kind of information. Apparently, something has happened. So, yeah. Well, regardless, welcome, gaming. Nice to see you in the chat. But maybe you are just sort of, gonna hang out in sort of the netherworld for a little bit. We'll see what happens. So yeah, well, welcome again all to to this live stream where we sit back and just share a common passion for the science of astronomy and science in general, nerding out on all kinds of things, right? Try to restrict ourselves, right, to sort of the astronomical groove, but tangents are definitely allowed for sure, because that's sort of how I roll too. Is that I like the tangents, especially if they're really interesting and leads to nice conversation. So, and speaking of conversation, I would definitely. I'm still trying to sort of push this idea of adding panel members down here. I think I can have up to 10 at one time, and I think as this channel grows. And I actually haven't looked at the number of subscribers yet. I think the last time I looked, it was about 140 or so, and it's sort of looking like I'm getting maybe 20 to 30 views per day, which I don't know if that is good or bad, because my motivations are different, right? It's just the simple fact that for years and years and years, I've been doing this exact thing. I've been sitting here in what is my evening time, get home from the day job, had some dinner, sit back, relax. What am I going to do? Of course, I'm going to think astronomy. So, for years and years and years, I've been doing this, practically every single day. And it finally dawned on me one day, probably late last year, right? It's probably actually that thought's probably started about a year ago or so. It's like, why don't I just share this passion and see what happens, right? And so here we are. So yeah, I think it's really fun and don't really have any kind of intentions beyond that. Anything else is sort of a secondary thing. So if this channel grows, okay. If it doesn't, if it stays exactly the way it is, okay. That's all right with me. So, because we here, seems to me, do share that common passion and want to think and talk all kinds of astronomical things. And this is sort of a format that is different than all the other live streams and podcasts and all that, in that it is very, very casual. There's nothing really planned or scripted or anything at all. Very authentic. The only thing that is different for me is that everything that you're sort of hearing during these live streams from me, I would usually just be thinking, right, as opposed to saying. I'm a really, really, really quiet dude, and yeah, so for me to talk at length at all is not really the norm. So that's really the only thing that isn't real. But all the thoughts are, it's exactly the same. So, all right. Anyway, let's see. I've got a little bit of coffee left here in a sort of a dirty mug. Inside, it's getting a little mucky in there, but I think I told you the story when I was a student at the University of Arizona, over in the astronomy department. One of the professors there and researchers there. I have his book. I've got his book somewhere. Anyway, and I'm pretty sure he is still alive. I'm pretty sure he may be retired now, but I don't think that John Cock would ever actually retire from astronomy. Anyway, he had a coffee mug that I am absolutely certain, right, hadn't been washed in years, right? Absolutely years, right? I mean, it was inside of the mug, right? Inside, right? Inside on the edge, right? It was like caked black, thick muck. Just really, really, really nasty, right? Really nasty. Like um, um, I can sort of imagine that if he would have taken this home, that you know uh, his wife, his kids, everybody would be like, look, wash that, wash that out. But he had it at his office, so nobody ever saw it, and so that's sort of my you know now the inside of mine is actually pretty clean at the moment, right? Um, but I use John Cock's coffee mug as a standard for how bad it can get, and as bad as mine can get, it's like nothing compared to his at all. And he drank out of it every single day, so it was awesome, very, very awesome. Anyway, so I've got the coffee here, so cheers.
Well, that extra in the cup just adds the flavor, right?
That's exactly it. There's just all those extra terpenes and flavonoids and who yeah, whatever else is growing in that thing. So yeah, he set my standard. Now I've got another standard that was set, a very high bar. Okay, now John Cock's coffee mug, that was a very high bar, right? Not to be easily surpassed, right? I mean, I've never seen anything that bad since, right? Well, there's another professor that was there and researcher. Now, look, these guys are like genius brilliant. I mean, like so far above us meager mortals, right? But all these geniuses have these weird quirks, right? And there was another professor and researcher who, like I said, absolute genius, right? Absolute genius. But Nick Wolf, who had an office right next to me, he, his office was, now granted, it was pretty small. It's pretty small. It was sort of tucked up in a corner. In fact, I think it was on a corner. But you open his door, right? And I think all the doors opened in, right? Because you have the hallways, so all the doors open in, right? And so you open his door, right? And you can't open it more than about halfway, because behind it is the beginning of these stacks of papers and manuals and books and, you know, little gadgets, you know, little um, like electronic things and you know, pencils and pens and notebooks and calculators, and his entire office was just these was just these stacks of just papers, and, you know, like I just said, but his whole office was just full, and there was a path, right, from the door to his chair, where supposedly he claimed that there was a desk there. So I don't think I ever saw that desk. Don't think I ever did. But you know, of course, he knew where everything was, and like I said, brilliant. Actually, um, pretty nice guy. There are lots and lots and lots of genius types who are creeps, right? They're just creeps. They might be brilliant. They might win awards. They may have, you know, all the honors and, you know, um, 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 accolades of the community, but they're creeps. They're absolute creeps. So yeah, there's all types. But yeah, so Nick Wolf set a very high bar in terms of how clean an office should be. And so, you know, I look around at mine here, and oh, it's, well, you know, I'm I, I'm definitely not going to give you a tour, because yeah, it is moderate a moderate amount of, you know, disaster area. But compared to Nick Wolf's, this is organized and clean. So so yeah, I was definitely taught by the best, for sure. So cheers to the best.
Yeah.
Let's see. So some WWE chat in the chat. Cool. Hey there, Totterbert. Nice to see you also in the chat. Dude. So yeah, you know, I my I th- at least how I sort of justify my mess is that if I actually wanted it, you know, the way that I sort of would like to have it, I would be constantly trying to straighten things out and organize and clean, and I wouldn't have any time for anything else. So it's sort of a compromise, right? It's like, okay, just you know, put the Burnhams on the floor right here, so when I need them, I can just grab them, right? As opposed to, you know, every single time, it's like I gotta, you know, go back to the shelf, pull it off the shelf, all that, and then I gotta put it back. It's like, no, you know, just put it on the floor. It's a lot easier. So yeah, that's just a, you know, mad scientist type of stuff. So you know, you either are or you aren't. That's all that's to it.
So it's an efficiency kind of thing.
Yeah, it's an efficiency thing. Easy is the operative word. So I like easy. That is one of my favorite four-letter words. Favorite. All right, well, cool. Let's, and Sanford agrees. Sanford agrees.
At least you're not being taught by a dummy.
Well, like I said, I had some very, very, very accomplished teachers when it comes to uh, um, uh, cleanliness and muck. So, all right. The astronomy days, the astronomy student days, so much fun, so much fun.
You ever had to clean around like the classrooms and stuff?
No, you know, I was a teacher's assistant for one semester, um, and that that uh, yeah, that was just you know, basically um, sort of being a tutor, um, which of course which I actually also did tutoring with. I think I did astronomy and math. What else did I tutor in? I think it was mainly just astronomy and math. So yeah, yeah. So but yeah,
That's what got you that jump to do astronomy and math, right?
what's that?
And that's what that got that jump to do astronomy and math, right?
Yeah, yeah. You know, I I was given the opportunity to get on as staff there, and yeah, that was an extremely easy jump. You know, one one has rare opportunities. Well, very very rarely, and that I easily recognized as sort of a once in a lifetime kind of a thing, and so yeah, that was a no brainer. That obviously set me on this path, which has been interesting. Yeah, for sure. All right, we were looking at stars and other objects in the constellation of Cetus. And what I wanted to do was I wanted to just sort of go back to the, in fact, I think what I want to do first, really, really quick, is go back to Burnham's and just sort of see if there's anything else, excuse me, that they mentioned. So hold on, see, I can just lean down and get it. Just like that. Very efficient. And go over to Cetus here. Centaurus, Cepheus. These are in alphabetical order. Cepheus, Cetus. Here we go. And what I wanted to do was I just wanted to see if they highlighted anything else that might be moderately interesting here. They usually like to talk about some of the brighter stars, you know, give a little bit of a history. So there's the info about Myra. We already talked about Myra. Let's see here. And then we talked about UV Ceti. I'm pretty excited about UV Ceti. Let's see. Oh, they have a finder chart here. That's kind of nice. Yeah, it'll make things a little bit easier. So yesterday we looked at M77 in not a huge amount of detail, but it's a nice galaxy, of course. And then they have pictures of a few galaxies here. Let's see, they've got. So this is NGC 1073, and NGC 157. It's these guys. There's some nice spiral galaxies. This one's it's got a bar in the middle, right? It's got a bar and then the spirals. So that's pretty cool. And then, let's see. Okay, so this is just, they're calling this members of the M77 group. Okay. So here's a couple others. Okay, so this is M77 itself. And then here's NGC 309. So the bottom one is NGC 309. And I guess there's M77 itself there. Nice. Nice. Oh, and then here's a couple more. NGC 247, another spiral. And Burnham's is calling it a dim spiral galaxy. And then there's the irregular galaxy IC 1613, which it says here is a member of the local group. So there's the top one, the NGC, and then here's IC 1613. And the local group is the cluster of galaxies in which the Milky Way is a part, and the Andromeda galaxy is a part. M33, I think, is a part of that. Of course, the large and small Magellanic Clouds.
How many galaxies are in the local group?
Yeah, that's just what I was trying to remember. I want to say there's something like 20 or 30, but why don't we just go and find out? Because, you know, new ones are sort of being discovered pretty often. So I've shared my screen, and I guess what I'm going to do is I'm going to go back to here, and, oh, not the news. No, we want regular Google here. We're forgetting about the news. What news? There's no news. There's only the universe. Local group. Galaxies. Local group. Local group is a galaxy group that includes the Milky Way. Oh, more than 54 galaxies. Wow, okay. I am behind the times. For sure.
54 galaxies? That's
54.
crazy.
Yeah. Well, you know, most of these are, I guess, what one would call dwarf galaxies. They're really, really small. So this is sort of a hard diagram to see, but here's the Milky Way, right? And you can sort of see all the galaxies kind of around it, right? And then we've got a few over here, and then a bunch around M31, and a few out around M33. But it's these three galaxies here that are sort of the main players. And then you got a bunch of dwarfs. So pretty cool. And, you know, I would not be surprised if we find more, right? I don't think that we're going to find any big ones, right? But we're probably definitely going to be finding a lot more smaller ones, for sure.
It's kind of a bit crazy that our local group spans within 8 million light years.
Yeah. Well, you know, like I said, you know, 8 million light years really isn't very far, relatively speaking. It's not really incredibly far. I mean, these galaxies are neighbors to us. They are right next door, right next door. And this local group here is actually part of a larger group, which is part of Virgo, and that goes at least I think a couple of 100 million light years or so, and maybe even more. So 8 million seems like a lot, and from a certain point of view, yeah, it's huge, right? But in terms of um, distances in the universe, 8 million light years. No, that is next door neighbors. Yep, right next door. So yeah, I didn't know that there were that many. So yeah, I'm glad we looked that up, because that's quite a few more than what I thought. And like I said, I wouldn't be surprised if we didn't find even more over time. It's just, these dwarf ones are pretty hard to see, because they're really, really faint. They're really, really sparse, right? Let's look up IC 1613, because that was one of those irregular ones. And in fact, let's look for that one on this map here. Can we find it? Let's see. IC 1613. There it is. It's kind of hard to read this map. I guess this is it right here. Okay. So I don't really know what direction that is, because, if we're sort of here looking towards Andromeda, that's looking up that away. And IC 1613 is sort of this away. So kind of hard to tell. But yeah, let's look up NGC or IC 1613 and see. I'm getting a little bit of echo, Bobby.
Okay.
Can that be mitigated in any way? If not, I'm not going to worry about it too much.
Yeah, just reset the mic.
Sinbad. Let's see if we can find this bad boy. IC 1613. Hey, there it is. Okay, so this is definitely an irregular galaxy, right? I mean, we're not really seeing any kind of structure or anything, not necessarily. Let's see here. We'll zoom out a little bit more. Pretty darn faint for sure. See if there's anything around it. Not seeing much. There's maybe a little bit of a galaxy here. But yeah, not too much. Everything I'm seeing is sort of foreground stars. Stars in our galaxy. Here's a maybe a satellite or something going through. Maybe blinking a little bit. Yeah, that's hard to tell. Hard to tell. Pretty cool though. There he is, real faint. Real faint. Let's see what else. Let's see what else this Sinbad has about this. Yeah, again, it's really, really hard sometimes to understand these magnitudes, right? Because especially with these extended objects, it's like, well, is this the magnitude of like the brightest star, or is this some kind of a combined magnitude, right? Where they've sort of, looked at the brightness of an area, added it all up, and said that's what the magnitude is. And I'm sort of thinking that that's what's happening in this case, because if this actually was a 10th magnitude object, we'd be able to see that in a 6-inch telescope. And I can assure you pretty well that you are not going to see this in a 6-inch scope at all. Period.
Check the chat.
Check the chat. Check the chat. Oh, the chat is busy. You like the mic stand? Yeah. Well, free hands. It's always nice. I can have one hand on the mouse and one hand on the coffee, and I am good to go. I'm good to go. Hey there, X-Universe TCAS. Nice to see you. You have joined a live stream show called Astronomy Daily Live, where each and every day we gather together and talk about all things astronomy. And it's just a very casual get-together of friends who share a passion. And at the moment, we are looking at a dwarf galaxy called IC 1613. And it's located in the constellation of Cetus. And it's a member of the local group of galaxies, of which the Milky Way is a member. So what I like to do is I just sort of like to go to this database, which is called Simbad, and it usually has all kinds of interesting information about these objects. And so, yeah, I've just decided to look at this today for a little while and see what happens. The first thing I'm going to look at is to see if the Sloan Digital Sky Survey looked at it, and indeed they did. I'm going to pull that up instead of just the regular Digital Sky Survey. Usually the resolution's a little bit better, and the colors look a little nicer, and yeah, that's pretty amazing. Now, I don't know about trusting these colors, right? I don't know how sort of true color this image is. Can't be exactly sure, without a little bit more info, which we're probably not going to get here. But there he is, IC 1613, for sure. Just sort of a loose association of stars, much bigger than a cluster of stars, but a lot smaller than sort of a regular, spiral galaxy. And something is going on here, right? You've got this big collection of stars here, and then you got all this stuff sort of flying off. Who knows? Who knows? Those are the mysteries that have to be solved. So let's see how much this object has been studied. Wow. Well, it's been looked at pretty hard, right? There's over 1,000 references to it. That's not too bad. Let's see how far away we think this thing is. Dun, 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 dun. It's trying. While it's trying, I'm going to take a sip of this hydrogen hydroxide here, HOH. Awesome molecule.
So each of those references is a paper that's been written on it?
Well, that's what it's supposed to be. Yeah, the references are supposed to at least mention this object. But what I've observed is that a lot of these references don't do that. So I don't know. Yeah. Okay, so they're saying about, what, about 750,000 parsecs or so. So a million parsecs is 3.26 times 10 to the sixth light years, right? 3.26 million light years. And sort of the average here, I'm going to say, is 0.75. All right, so I'm going to multiply that by 0.75, and we get 2.4 million light years away. So it's about the same distance as the Andromeda Galaxy is, at least according to the measurements that we're seeing. See you later, Todderbert. Thanks for coming in. Looks like the velocities sort of agree. These might be in different units, which is why the numbers are so different. But kind of interesting relative to us, right? We and this galaxy are moving towards each other at what, about 240 kilometers per second or so. So that's kind of interesting. Let's see if I'm just sort of curious to see if Google has anything to say about IC 1613. I doubt it, but let's find out. Oh, wow. Okay. I stand corrected. For sure. Let's see, anything. Yeah, see, this is giving it a magnitude of 10 as well. And I gotta say that has got to be sort of a combined magnitude. But, you know, given that it's so close, I suppose it could be that bright. I don't know. It says here that it's played an important role in calibrating the Cepheid variable period luminosity relationship. So there are apparently Cepheid variable stars in this galaxy that we can observe, and because it's so close, we can sort of, you know, get a handle on that kind of relationship. So that's kind of cool. So this has been observed with the HST. That's kind of interesting. Maybe we should go look over there too. So the dominant population of stars is about 7 billion years. 7 billion years. Okay. Kind of cool. Let's see what HST has to show us here then. IC 1613. We'll do all images and all spectra and everything in between. Yeah. Wow. Okay. It was, well, I guess not recently observed, but oh, okay. Well, there's some new ones that we probably don't have access to yet. So, I wonder what these guys were doing. Using the wide field camera 3, looking in sort of the ultraviolet. Let's see what they were up to here. We can look at their abstract. Ultraviolet imaging of the stellar populations of a volume limited sample of 22 low mass nearby star forming galaxies. Cool. So they're trying to measure luminosities temperatures, dust extinction. Cool. Nice. Yeah, so they're doing all kinds of stuff here. Looks like they've gotten a lot of data in the past. New insight into the baryonic physics of galaxy formation. Sweet. Well, let's hopefully that data will be made available sometime, at least. For now, we're going to have to wait. Most data that comes from like the HST or most government-funded programs like this, the data is usually sort of accessible only to the principal investigators for like maybe the first 6 months or the first year or two. They put in the effort. They've done the work. They have the questions. So it seems only right that they should have access to the data first, right? But after either a certain amount of time or when the PIs are sort of done with it, then if this was a publicly funded project, then that data for sure should be made available to the rest of us, because it's ours. Let's take a look here. So I don't know what the COS instrument is. Guess we're going to find out. It looks like it's a spectrometer of some sort. So pretty high-res spectra here, for sure. Looking in the ultraviolet, right? So this is going from what, about 1170 up to about 1310 angstroms, and then what, from about 1330 to 1470 or so. And we're definitely seeing absorption lines here. Maybe some emission, kind of hard to tell. It's a little noisy, but not too bad, I guess. And they actually have this in units of energy per time, per area, per wavelength. So it's kind of an interesting way of looking at the flux over here, but that's pretty standard. And we're definitely seeing some structure. Again, I am not even going to try to interpret this, but I can say, right, that the depth of this absorption, the widths here, all of that can tell us lots of interesting things. We can sort of infer lots of things from that kind of information. Spectra are absolutely fantastic. I think at some point I should maybe get into the analysis of spectra a little bit more. That again is a that kind of work can last years, but it could definitely take 2 or 3 or 4 live streams to go through all of that. But yeah,
I think an overview would be very helpful to some of us.
Yeah, because spectra tell us so much more than pictures do. Pictures are great, right? But they're limited in terms of the information they can provide. All the information in those pictures, except for the astrometry, right, the positions of these objects, are contained in the spectra, right? So, all the photometry, all the polarimetry, and then, all those inferred values like temperature and how much stuff is there, what stuff is there, how fast they're moving, how they're moving, even like how far away they are. There's all kinds of interesting information in these things, but it's tough, right? I mean, this is some tough stuff. But I can say that most of these wiggles do probably have some kind of a significance, right? Noisy as they are, um, uh, these things all have at least a little bit of meaning behind them. So here's the wide field camera 3. Let's take a look here. I'm not quite sure why some of these are blocked out, but this one isn't. Right, so this was taken on the 20th of December 2011 at a central wavelength of 3897 angstroms. So let's take a look here, and it was with the wide field camera 3, so well, maybe we'll have a interesting picture to look at. This is a pretty sparse galaxy. So we're not going to see much, but quite a few stars here. We have to look and see exactly what these guys, we're looking for here. I'm not quite sure if that's a background galaxy or some kind of nebulosity. Here's another little satellite going through there. Always got satellites in all the pictures.
You blacked out on the feed.
Did I? Well, humblest apologies. Hopefully I'm back. Hopefully. So let's see. Let's.
Yeah, you're back.
Good. So these are pretty long exposures too, right? 5,240 seconds. What is that? 5240 divided by 3,600 seconds per hour. It's almost 1.5 hours. So an hour and a half long exposure here. Wow. Okay. Well, I hope they got what they wanted, because I'm seeing a bunch of stars and all that. Let's sort of see what they were after here. We can look at the proposal here again. 12304. We will measure metallicity distribution functions in 4 local group dwarf galaxies. Using a medium band filter available with wide field camera 3 that covers the calcium H and K lines. Okay, cool. So they were looking at calcium. To astronomers, there are only 2 elements. There's hydrogen and metals. So, oh, I'm sorry. Yeah, anything that isn't hydrogen is a metal. So when you look at the metallicity of things, you sort of have to look a little bit harder to see. It's like, well, what metal are they talking about? It looks like in this case they're talking about calcium, which yes, is definitely not a metal. But
so they're including helium as a metal?
I'm thinking that maybe they do. I'm thinking that maybe it's just hydrogen, and then everything else is a metal. I think. So helium might be included in that. Not quite sure.
It's a different way of looking at it, I guess.
Well, astronomers do have a different way of looking at things. So yeah, I guess what they're doing is they're measuring metallicities by looking at their differences in colors. So it's sort of not as good as spectroscopy, but okay, that's what they decided to do. Go for it. Interesting thing is that, well, okay, yeah, that's not true. It does look like they looked at this object at a bunch of different wavelengths, right? All the way from the infrared into the ultraviolet, and sort of everything in between, right? Here's a 5305 angstrom. Here's an 8048 angstrom. So this is sort of a little bit green. This is pretty red. These are definitely in the infrared. 15,000 angstroms. Here's an 11,000 angstrom one down here. So let's look at this thing in the red. I mean, we're not going to see much of a difference, I don't expect. Maybe a little bit of dust. I don't know. Okay. We're seeing, I guess we're looking at some background galaxies here that have popped out in the infrared. That's kind of interesting. Let's see, I'm going to get rid of that. So that was at infrared wavelengths. Let's look at sort of red here. See if there's much of a difference. Okay, just seeing less of the background galaxies. Here's one in the visible, right? Pretty much right in the center of our visual range. And yeah, we're just seeing a bunch of stars, a bunch of galaxies. I think, let's see. Wow, see, it's totally amazing. It's this hour has almost gone by already. It's incredible. What I was thinking about doing was grabbing a few of these and throwing them into GIMP. Not going to see much, I mean, these galaxies will pop up and sort of be able to see, the colors of the stars and everything else. But I'm sort of looking at the time and trying to be mindful of that. See anything else interesting here? 3897. Let's see. So this is more towards the ultraviolet again. Okay. Yeah. Shoot. I think we can sort of do this a little bit quick. So let's see. Let's pick out some candidates here. So let's look at the 3897 one. Okay. That's this one. Okay, so let's save that. I guess it'll ask me where I want to put it, and I guess I'll put it here. Let's see, we'll call it 18105. Okay, so this one I'm just going to call image 001. So these are just JPEG images. This is not the FITS data, the actual scientific data. We're just sort of messing around. So I grabbed that one. Let's grab an infrared one. How about, we haven't looked at that one yet. Yeah, so let's grab this one. Hopefully these are pretty well co-stacked. I'm hoping that they are because it's the same instrument. Well, one can hope. One can definitely hope. I don't, well, guess we're going to find out. Image 002. And then how don't we grab this one that was at 5,300 angstroms? Yeah, I don't think those are on the same scale. I don't think that infrared one, I think, is not going to be on the same scale as these other two. Why don't we look at the 80481 then? Let's see if those are on the same scale. Come on. I think those are. So let's 004. Look at that galaxy there. Isn't that nice? It's a nice, looks like a edge-on. It has a dark lane through it. Yeah. Okay, so let's see. Let's go over here. And I'm going to go up to here. Astro. Live. Yeah, see, I think 1, 3, and 4 are all the same, but 2, yeah, it's not the same scale. So, all right, let's open up GIMP here. And take a quick look. So we'll load that one, and then we'll load the other two in a couple other layers, 3 and 4. That. Okay, and maybe we'll order them that way. So let's see, the first thing is, let's go into RGB mode, and I'm going to make this a little bigger. Let's go like 33. Yeah, there we go. So let's invert this. And we'll invert this one. And we'll invert this one. Okay. And then let's sort of stack them all up here like that. See, so now, yeah, those look like they're pretty nice and stacked on top of one another. Let's sort of see here. Kind of hard to tell. Oh, that maybe is a little bit off. Yeah, that's a little bit off, I would say. So let's be just a pixel or so. There we go. See how that, you sort of look at like this star here. See how it goes from that to that to that. So I'm sort of thinking that's probably about right. So yeah, they were a little bit off. Nobody's perfect. Let's see. So image one was the, oh, no, I'm not remembering, of course. Image one was the infrared one. What are you doing there? Or, I'm sorry, the ultraviolet one. So let's make that one blue. So I'm just sort of arbitrarily going to assign these 3 images colors. We'll make that one blue. And let's see. Oh, that's why I did that. Okay. I think the next one was sort of in the middle, so let's make that green. And then we'll make the other one red. So let's make this one green. Colorify. And we'll make this one red. see what that does. Just some simple colorifying. Well, that's pretty nice. Makes those galaxies really pop.
Now that looks like a perfect picture.
It's pretty. These are very, very blue stars. Look at that. Isn't that amazing? Very, very blue. But yeah, then you've got all these little galaxies behind here that are red and orangey and everything else. Here's that that really, really faint edge-on spiral right there. Let's zoom in on him. You see that nice dark lane through there now? Yeah, that's stacked up pretty nice, gotta say. And what these researchers would do, of course, is they would look. They'd look at the differences in brightnesses between these three pictures, and from that you can sort of infer things like metallicity, for sure. So pretty nice, pretty nice. I think that is definitely a keeper. Kind of hard to see the dwarf galaxy, though. I'm sort of assuming that this group of stars might be a part of it, and maybe all these blue guys down here are. Kind of hard to tell. Well, so it looks like there's a bunch of blue stars here too. So yeah, don't know. But you know, the HST is a pretty nice instrument because it doesn't have any of the atmosphere to deal with. So yeah, we get some nice sharp images out of that. And yeah, there's quite a few galaxies sort of behind this one, for sure. I wouldn't say that any of these are really part of the local group or anything like that. You know, they look like spirals. This is an elliptical galaxy, it looks like. Maybe seeing some nebulosity here. Kind of hard to tell. These images, you know, would have to be cleaned up a little bit, and yeah, hard to tell exactly. But I guess from this, they can at least make a couple of guesses in terms of metallicity. So pretty nice, pretty nice. Let's merge these, and then I can play with the brightness and contrast a little bit and see if we can dig anything else out here. Not seeing much. Yeah. Not anything too exciting, I guess. That's a nice shot, though. And, you know, bottom line is, hopefully, this data provided them with the info that they needed to do their work. That's what it's all about. Sometimes the proposals will. Okay, yeah, here we go. So, let's see. Who was this? Holtzman, John Holtzman, but this paper was written by Ross. Let's just sort of look at the paper here, see. Over on archive. There he is, John Holtzman. So that That's who actually proposed the HST time. So he's on the paper, second author. So that's nice. So, well, yeah, we're running a little bit over, but I guess that's how it goes. Following our noses here. That's what science is. It's like, oh, what's that? Oh, what's that? So this was written. Draft version 2018. Wow. So this is pretty new. Let's see. Do we have some? Let's see. December 16th and 20th of 2011. Yep, 16th and the 20th. Yep. Actually, even slightly into the 21st here. See that? They didn't include that there. Shame on them. So yeah, it's sort of, they're talking about looking at this in 3 wavelengths, right? 390 nanometers, 555 nanometers, and 814. So, and those are the 3 colors I think that we grab to make the picture. Let's see. Yeah, see, so they are just looking at the brightness differences, right? So they measure the magnitudes of, particular objects in the field of view, stars. And they measure the brightnesses of all these at these different wavelengths. And then if you look at the differences between those, that, can give you an indication of temperature and size and mass and age. Yeah, I mean, some of those are a little bit of a stretch, but okay. And I'm just flying through this because I'm looking for plots.
Those are my gruesome. Cheers.
Hey there, I grew some. Nice to see you in the chat. Okay, so here's a, oh yeah, I'm not going to do too well in sort of interpreting this rapidly. But here are the measurements they made, and the red squares are from our galaxy, that we're looking at here, IC 1613. So it looks like they picked out a bunch of stars. It's quite a few there. Kind of interesting. Yeah. Again, I mean, we'd have to sort of dive into the paper a little bit to really know what they're doing here, but it definitely looks like they use this data, these images, this photometric data. 721 kiloparsecs is what they're saying. Let's see, without data on the proper motion. So here, yeah. As I said, I'm not gonna try to interpret this too much on the fly. I just sort of like looking and seeing what we can sort of pull out. I'm not quite sure what the M here and the M divided by H, this is some kind of metallicity measurement, but yeah, I can't be exactly sure. What else does it say here about 1613? Accretion plus truncation model. The accretion parameter of m equals 3.7. Yeah, I don't know what any of that means. That's flying over my head for sure. Okay. Well, what else do we have here? Anything incredibly interesting? Here's another plot of some sort. The gradients are in units of dex of m divided by h. Oh, wow. Yeah. Phew. That's some heavy thinking there for sure. It's amazing, how much work goes into these papers, and the amount of knowledge is just, it's staggering. It always just blows my mind, that people can think this way, and really understand, or at least think they understand what they're talking about. It's fantastic. All right, well, we are definitely past time, so I am going to stop sharing the screen, get back onto this. I'm going to check the chat really quick, make sure that there are no other shenanigans. All right, cool. All right, well, I'm really glad you all came in. It's always nice to see everybody in the chat. Panelists too, very awesome. Tom and Bobby, thanks for coming in. And
Not a problem.
yeah.
Thank you.
You all have a great evening, a great day. Make sure to subscribe if you haven't. You can hit the thumbs up, thumbs down, whichever you prefer. Make some comments. And more than anything else, spread the word. Spread the word. I'm here, just sharing the passion, and not necessarily here to teach anything or communicate science or anything. I'm just sharing the passion, and I think all those other things actually just sort of happen. Don't really even have to try. So all right, I think it is time to go for now. So I will see you all again in just a little less than 23 hours from now. Just about one spin of this tiny little planet we're on. Tiny little thing. But yeah, it's all we've got at the moment. So hang on to it. Hang on. All right. Take care, everybody. I will see you later. Okay. Bye.
Later.